So hello everyone, welcome to the Gate Wallah and good evening everyone, very good evening to all of you. So on Monday we started the fault analysis of the power system and I told you the different type of fault that may occur into the power system. It may be series fault, it may be the shunt fault. Mainly we will keep our discussion only for the shunt fault. The shunt fault can further classify into the two category. It may be the symmetrical fault or it may be the unsymmetrical fault. We have already discussed in detail about the symmetrical fault. Symmetrical fault is a fault in which all the three phases are involved. Now we are discussing about the unsymmetrical fault. Unsymmetrical fault is a fault which involve either one phase or the two phases. So the first fault we are discussing is the line to ground fault. In the line to ground fault, the one phase is the short circuited to the ground. I told you whenever the line to ground fault occur, all three, that means the positive sequence, zero sequence and the negative sequence current flow into the picture. Whenever the line to ground fault occur, the positive sequence network, negative sequence network and the zero sequence network are connected in series with a 3ZF impedance, where ZF is a fault impedance. So in which way you can find out the value of fault current, and the value of fault current was 3 divided by Z1 plus Z2 plus Z0. So let's move to the line to ground fault further. Yesterday, in the yesterday class, I discussed about the unsymmetrical fault. What is the meaning of unsymmetrical fault? Then I told you regarding the sequence network, what is the positive sequence network, what is the negative sequence network, what is the zero sequence network, how we can draw these network. Then I told you how to analyze a power system when line to ground fault occur into the system, how we can find out the fault current during the line to ground fault. Yesterday we also do the comparison between the line to ground fault and the three phase fault. That means suppose if the fault occur near to the alternator terminal, if the fault is occurring at the transmission line, then which fault is more severe? We have done all this in the yesterday class. Now in the today class, we will do certain more question on the line to ground fault. Then we will analyze the power system when the line to line fault occur into the system. That means when the two phases are short circuited, how we can find out the fault current. After analyzing the power system during line to line fault, we will do certain question for line to line fault. Okay, so let's move. So this is a question from line to ground fault. The question say the severity of line to ground and the three phase fault at the terminal of unloaded synchronous generator is the same. That means the fault is occurring at the terminal of synchronous generator. If the terminal voltage is 1 pu, 1 pu means the nominal voltage, x1, x2, that means the positive sequence and the negative sequence reactance of alternator is J0.1 and zero sequence reactance is the J0.05 pu for the alternator. Then the required inductive reactance for neutral grounding is, that means you have to find out the value of Xn, the neutral reactance, so that the fault current during line to ground fault and and the three phase fault remains same, because the severity of line to ground fault and the three phase fault is same. For which value of Xn, you have to find out the value of neutral reactance. What will be the value of neutral reactance? So let's do this. See, if I find out the fault current during the three phase fault, it is nothing but the E divided by Z1. Only positive sequence impedance I will take. Z1 is the reactive in nature, so I will take the X1 only. Clear? Now the fault current for line to ground fault is nothing but the E upon X1 plus X2 plus X0. If the neutral reactance is also there, then you will take X0 plus 3Xn. This is become overall zero sequence reactance of alternator. Clear? This X0 is the zero sequence reactance of alternator plus 3xn. Xn is a neutral reactance. This is the 3E. Now, for which value of Xn, this fault current and this fault current will remain same. Clear? So, let's equalize these two current. So, it is become the fault current for the three-phase fault should be equivalent to the fault current for line to ground fault. Three-phase fault is nothing but the E upon X1, and this is the 3E upon X1 plus X2 plus X0 plus 3xn. Now, the E and E will be cancelled out. So, finally, the 3x1 is equivalent to x1 plus x2 plus x0 plus 3xn. So, what is the value of xn? The value of xn is become 3x1 minus x1 means 2x1 minus x2 minus x0 divided by 3. For this value of neutral reactance, the fault current for line to ground fault and the three-phase fault will remain same. Put the value of x1, x2 and x0, 0.1, 0.05. So, 2 into 0.1 minus 0.1 minus 0.05 divided by 3. So, 0.2 minus 0.1, 0.1 means 0.05. 0.05 divided by 3. It is nothing but the 0.01666. So, if the value of neutral reactance is equivalent to the 0.01666, then the severity of three-phase fault and the line to ground fault will remain same. So, which is the correct answer? 0.0166. A is the right option. Yes. Tell me any doubt in this? Any doubt? Clear? Okay. So, let's move to the next question. So, here we have a two question which have the common data. The common data for the next two question. At a 220 kV substation of the power system, it is given that the three-phase fault level is the 4000 MVA. The three-phase fault level is given and the single line to ground fault level is a 5000 MVA. So, fault level for the three-phase fault as well as for the single line to ground fault is given. Neglecting the resistance, we will consider only reactance and the shunt susceptance of the system. The positive sequence driving point reactance at the bus is, what is the positive sequence reactance at the bus? That means you have to find out the value of x1. See, the fault level for the three-phase fault is given and the fault level for a line to ground fault is given. In the three-phase fault, only the positive sequence circuit come into the picture. So, we can find out the positive sequence reactance only by using the three-phase fault level. So, three-phase fault level for three-phase. What is the fault level? That means the fault MVA. It is in the MVA. So, I will use the root 3 pre-fault voltage. That means the rated voltage multiply by fault current, because it is in the MVA, it is not in the PU. So, I will take the root 3 into account. So fault level is a 500 MVA, 5000 MVA. That means the 5000 into 10 raised to the power 6. Root 3 pre-fault voltage means the nominal voltage. See, this is the line voltage. Root 3 line voltage, line current. So line voltage is a 220 kV. It is a 220 kV substation. So the pre-fault voltage will be the 220 kV. 220 into 10 raised to the power 3. So this is the fault current for the three-phase fault. So this will be the fault current for the three-phase fault. So I can find out the fault current for the three-phase fault is nothing but the 5000 into 10 raised to the power 6 divided by root 3 into 220 into 10 raised to the power 3. Calculate the value of fault current. So it is a 5000 divided by 220 into root 3. That is 13.12 kilo ampere. 13.121.6. Clear? Or you can say if I do 121.6 ampere. But we have to find out the value of positive sequence reactance. This is the fault current for the three-phase fault. So now I will apply the formula. The fault current for the three-phase fault is nothing but the E upon Z1, or now it is a X1, because you can neglect the value of resistance. See, here the E is always the per phase basis, because I told you the sequence network means the positive sequence network, negative sequence network, or the zero sequence network is always the per phase network. It shows the voltage between a single phase with respect to a reference terminal. So always remember this thing. This E will be always the per phase voltage. This is the per phase voltage. Do not commit any mistake here. E. Now 220 is my line voltage. In the three phase, the given voltage is always the line voltage. So 220, that is the 220 into 10 raised to the power 3 divided by root 3. It is a phase voltage. Multiply by X1. And the fault current, I already got 13121.6. 13121.6. So find out the value of X1. 220 into 10 raised to the power 3. 13121.6 into root 3. That is a 9.68. 9.68 is the right answer. 5000 MVA, 220 kV. Let me check one again. 5000 000 divided by 220 into root 3. This is 13121.6. One 13121.6 into under root 3. Yes, it will be 9.68 ohm. So this will be, you can take this is a 9.68 ohm. So now the D is become correct answer. 9.68 ohm will be the correct option. The positive sequence driving point reactance at the bus is become the 9.68. Clear? Any doubt in this? So first you have to find out the value of the fault current, and from this fault current value you can easily find out the value of positive sequence reactance. Now The second part of this question is you have to find out the zero sequence driving point reactance at the bus. What is the zero sequence driving point reactance? Yes, try to solve this. Sorry, we have done one mistake here. The fault level for the three-phase fault is a 4000. So take it as a 4000 and repeat this question. 4000. It was a 4000. Clear? So the fault current for the three-phase fault will be 4000 into 10 raised to the power 3 root 3 into 220. Four thousand 123. It is a 10497.27. 10497.27. 10497.27. It is a 10497.27. Now calculate 220 000 10497.27 into under root 3. That is a 12.10. Yes, 12.10 ohm is the right option. 12.10 is the right option. Clear? Okay. Now, in the second part of this question, you have to find out the zero sequence driving point reactance. So see, in the question, the fault level for three-phase fault is given. Now the fault level for the line to ground fault is also given. So I will take the fault level for line to ground fault to calculate this. So for line to ground fault, the fault level will be, again the fault level is given into the VA, that means the actual quantity. So you will take the root 3 into pre-fault voltage multiply by fault current. Now this fault current is for the line to ground fault. So for single line to ground fault, it is a 5000 MVA. 5000 MVA. So it is a 5000 into 10 raised to the power 6. Root 3. Pre-fault voltage is the nominal voltage is the 220 kV. By using this, you can find out the fault current for the line to ground fault. So what will be the fault current for the line to ground fault? Line to ground fault. That is the 5000 into 10 raised to the power 6 root 3 220 into 10 raised to the power 3. 5000 divide by 220 into under root 3. That is a 13121.6 ampere. This is the fault current for line to ground fault. You have to find out the zero sequence reactance. Now use the formula of fault current for line to ground fault. So the formula for line to ground fault is nothing but the 3E divided by x1 plus x2 plus x0. All the three sequence network are connected in series. Until unless it is given, if you do not know about the negative sequence reactance, you will assume that the x1 is equivalent to x2, because for cylindrical rotor alternator, the x1 is equivalent to x2, and for the salient pole alternator also, the x1 is approximately equivalent to the x2. So if x2 is not given, so we will take x2 as a equal to x1, and I just find out the value of x1. The value of x1 is the 12.10. It is nothing but the 12.10. So this is 13121.6. 13121.6. This is the fault current for the line to ground fault. 3E. E is, again I told you, always take the E as a per phase voltage, and the per phase voltage here is 220 kV. So 220 kV, 220 into 10 raised to the power 3 divided by root 3. x1 plus x2 plus x0. Now we know the value of x1 x2, then you can easily find out the value of x0. Clear? So x1 plus x2 plus x0 is the root 3 into 220 into 10 raised to the power 3 divide by 13121.6. Now calculate this. .04. It is a 29.04. x1 plus x2 naught plus x is the 29.04. So finally x naught is nothing but 29.04 minus x1 minus x2. 29.04, x1 and x2 12.1. So 12.1 minus 12.1. 24.2. That is the 4.83. Even 4.84 ohm is the value of x naught. .84. B is the right option. Is it clear how we can find out the value of positive sequence reactance and the zero sequence reactance if the fault MVA is given to us? So we require the fault MVA for the three phase fault and the fault MVA for line to ground fault. Okay. Now come to the next question. What will be the subtransient fault current in each phase for a dead short circuit on one phase to ground? That means for the line to ground fault, you have to find out the fault current at the bus number Q. This is the bus number Q. This is bus number Q. So here directly, see, this is the single line diagram of a power system is given. Here directly the positive sequence impedance or negative sequence impedance is not given. Here the positive sequence impedance, negative sequence impedance and the zero sequence impedance is given for the different component present into the power system. So by using by this question you will know how we can draw the positive sequence network, negative sequence network and the zero sequence network. So we will draw the positive sequence, negative sequence and the zero sequence network, because in the line to ground fault we required all three type of network, and these three network will be connected into the series. Then we have to find out the positive sequence network, positive sequence impedance, Thevenin equivalent impedance, a negative sequence Thevenin equivalent impedance, and the zero sequence Thevenin equivalent impedance. Clear? So this is my source, a transformer connected in the delta star is grounded, a transmission line, then again a transformer star delta, and this is a synchronous motor, or it may be the generator. See, the subtransient reactance is given. This will be, you will take it as a positive sequence, this is a negative sequence, and this is a zero sequence. Similarly, this is a positive sequence subtransient reactance, a negative sequence reactance, and the zero sequence reactance. So first you have to draw the positive sequence network, a negative sequence network, and the zero sequence network. So let me try to draw the positive sequence network first. Okay, how we will draw the positive sequence network of this system? That means I will draw the reactance diagram. First I am taking the alternator. How I will draw the alternator? Alternator is nothing but there is a source in series of a reactance. Clear? If you take this is a zero potential bus, that means it is a reference and this is a phase. You will take this is a positive sequence reactance only, and this is nothing but the 0.16. So subtransient positive sequence reactance is the J0.16, and the induced EMF is nothing but 1 angle 0 degree. So this is my positive sequence network for the alternator. Now, how to draw the positive sequence network for a transformer? I told you we will draw the positive sequence network for the transformer. Transformer equivalent circuit will like a reactance only. So this is the positive sequence network of a transformer. I will take the positive sequence reactance here. That is the J0.10. So it become J0.10. Clear? Now, after the transformer, there is a transmission line. Again, we all know that the transmission line is also represented as a reactance only. We will neglect the resistance and the shunt branch parameter. Its positive sequence reactance is the J0.11. So it is a J0.11. Clear? Alternator, transformer, transmission line. After the transmission line, again there is a transformer. See, this is a bus. So here we have a bus Q. This we have a bus Q. And after this Q point, there is again a transformer. So transformer again you will represent as a reactance. You will represent as a reactance transformer. And this is the J0.10. J0.10. Now finally, the next synchronous machine. The synchronous machine will be represented as a source and a reactance. Source is again 1 angle 0 degree, and the reactance is a positive sequence reactance, which is J0.10. Sorry, J0.2. J0.2. So this is connected together. You can say this is the reactance diagram or the positive sequence network for the given circuit. Clear? Now we have to find out the Thevenin equivalent positive sequence reactance from the fault point. So where the fault takes place? The fault is occurring at the bus Q. So fault means this phase will be short circuited with the zero potential bus. Now, if you find out the Thevenin equivalent impedance from this point, this will be overall the positive sequence reactance. Clear? The Thevenin equivalent positive sequence reactance at the fault point. So, to find out the Thevenin equivalent reactance, we will turn off this voltage source. Turn off means just short circuit this voltage source. Now 0.10 0.11 means 0.21, 0.21 and 0.21 and 0.16. That means 0.37. So this is the 0.37. J 0.37. And here impedance is become 0.10, 0.2, 0.30. J 0.30. Now, just find out the reactance across this terminal. So 0.37 and 0.37 are 0.37 and the 0.30, they are in parallel. So it is become 0.67. So overall, the positive sequence reactance will become 0.37 into 0.30 divide by 0.67, 0.16567. Clear? Zero 0.16567. This is my equivalent overall positive sequence reactance at the fault point. Now, let's draw the negative sequence network. The negative sequence network. Let's draw this. The negative sequence network does not have any source. So the negative sequence network of this is nothing but a reactance of J 0.17. J 0.17 is the negative sequence reactance of the alternator. It does not have any source. Now, the negative sequence network of a transformer is again simply reactance of value 0.10. 0.10. 0.10. Clear? Now, for the transmission line, the NSN for the transmission line is again simply reactance of value 0.12, because the negative sequence reactance is again 0.11, sorry, 0.11, J 0.11. Now, the negative sequence reactance of this is a reactance of J 0.10. J 0.10, and the negative sequence network for this synchronous machine is having a reactance only of value 0.22. 0.22. The negative sequence network does not have any source. Clear? So this is the overall negative sequence reactance diagram. Here we have a Q point. So the fault occur here. Now from the fault point, find out the equivalent reactance. So what will equivalent reactance? 0.21, 0.21, 0.17. That means the 0.38, 0.38. And this is 0.10, 0.23, 0.32, 0.32. Now, find out the equivalent reactance here. Zero 0.38 into 0.32, and it is a 0.70. 0.38 into 0.32 divided by 0.70, 0.1737. 0.37 is the overall negative sequence reactance at the fault point. Clear? Now draw the zero sequence network. Especially take care while drawing the zero sequence network for the transformer. Okay, now I am going to draw the zero sequence network. How to draw the zero sequence network? Again, I already told you, in the zero sequence network of the alternator does not have any source. It is having only a reactance. The reactance whose value will be the zero sequence reactance value 0.06 J 0.06. Now there is a delta star transformer. I told you the zero sequence of a three-phase transformer is like this. Primary winding is delta connected, so this circuit will be closed. Secondary winding is star connected with the grounding, so this will be closed. So it will be like this. This is my equivalent circuit. Clear? So it will be like this. This. Its value is the J 0.10. After that, line of reactance 0.33. 0.10. Now J 0.33. Clear? Again, I will draw the zero sequence network of star delta transformer. Again, what you will do? Primary winding is star grounded, secondary winding is delta. So it will be like this. It will be like this. So it will be like this. Connected, but here it is open. And then the synchronous machine. Synchronous machine zero sequence reactance is a 0.15 and this was the 0.10. 0.10 J 0.15. The fault occur at the Q terminal. This is the Q terminal. This is the fault point. Now find out the Thevenin equivalent zero sequence reactance. So how you will find out? Now you can say this and this are connected in parallel. So X0, the value of X0 will be 0.33, 0.10, 0.43, 0.43 and 0.10. 0.43 into 0.10. 0.0811. 0.0811. Clear? So I got the value of x1, x2, x0. Now just find out the value of current, fault current for the three-phase fault. So, sorry, line to ground fault. So it is a 3E divided by x1 plus x2 plus x0. E is a 1. So x1 is 16567 J 0.16567 X2 1737 and 0 sequence 0.0811 0.0811. Three divided by 0.16567 plus 0.1737 plus 0.0811. 7.13 PU. Check the calculation once again. Yes, it is correct. 7.13 is the correct answer. Is the right option. Clear? So this is a bigger example, but I told you how we can find out the positive sequence network, negative sequence network, and the zero sequence network. And for a bigger type of problem, how you can find out the fault current when the line to ground fault takes place. So for that, you have to draw the positive sequence network, negative sequence network, and the zero sequence network. So while drawing the positive sequence network and the zero sequence network is not a difficult task, but while drawing the zero sequence network, you have to take care for drawing the zero sequence network for a three-phase transformer. So you have to see whether the primary and the secondary winding are connected in the star or delta, or the star is grounded or not. This is clear. So this was my first unsymmetrical fault, that is called the line to ground fault. Now I will move to the second type of unsymmetrical fault. This is the line to line fault. So in starting, I told you there may be the three type of unsymmetrical fault occurs into the power system: line to ground fault, line to line fault, and the double line to ground fault. So we have already discussed about the line to ground fault. Now we move to the line to line fault. In line to line fault, the two phases of the three phase line are short circuited. It may be the bolted fault, or it may be the short circuited through the fault impedance. So I am taking a general example where these two are short circuited by a fault impedance. When the line to line fault occurs into the power system, then which sequence network come into the picture, and how we have to connect these sequence networks to find out the value of fault current. Let's analyze the power system. So this is my power system. This is a alternator. After the alternator, there may be the transformer and the transmission line. Suppose at this point there is a phase to phase fault. That means the B phase and the C phase are short circuited, but it is not a bolted fault. It is a short circuited by a fault impedance ZF. It may be directly short circuited without any fault impedance. Clear? So ZF is a fault impedance, and we are assuming again that before occurrence of the fault, no current was flowing. Okay, this was my assumption. That means the current will start flowing only after occurrence of the fault. No current was flowing before fault. Before occurrence of the fault, no current was flowing. Now, after fault, no doubt, the A current will be equivalent to the 0, but the B phase and the C phase current will be flow. And you can say B current and the C current, they are equal in magnitude, but they are in the opposite direction. That means the IB is opposite to IC. This is the IB and this is the IC. So IB is equivalent to minus IC. So during fault, the value of IA current is equivalent to 0, but IB and IC are same, but they are opposite to each other. And what is the fault current? This is my fault current. So fault current is nothing but the IB. So fault current is either IB or it is a minus IC. Clear? So this is the phase current during the line to line fault. Now, if we apply the KVL here, I am moving from this point. VB minus IB ZF is equivalent to VC. So VB minus IB ZF is equivalent to VC, or you can say the VB is equivalent to VC plus IB into ZF. So I will use these current equation and this voltage equation to find out the sequence currents and the sequence voltage. So let's do. Now the relationship between sequence current IA0, IA1 and IA2 and the phase current is related by a inverse matrix A, 1 1 1 1 A square 1 A square A. IA, IB, IC. IA, IB and IC. Now, IA is 0 and IB and IC are opposite to each other. Clear? So, I will put this IA is equivalent to 0 and this IC is nothing but minus IB. You can say it is nothing but the minus IB, or you can say IB is equivalent to the minus IC, whatever you can say. Now, the IA 0. See, 0 IB minus IB, 0 plus IB into minus IB, 0. That means the no zero sequence current is flowing. So whenever line to line fault occurs, then no zero sequence current will flow into the circuit. So no zero sequence current will flow. No zero sequence current will flow. Now, the value of IA1 1 upon 3, no? It is a 1 upon 3, 0, AIB, A square IB. That means the A minus A square into IB. Then IA2, 1 upon 3, 0, A square IB minus AIB, A square minus AIB. Now you can write this as a minus 1 upon 3 A minus A square IB. So this is equivalent to IA1. So IA2 and IA1 are opposite to each other. Clear? So what we got? The IA0 is equivalent to 0, but IA1 and IA2 is opposite to each other. No zero sequence current is flowing, and the positive sequence current and the negative sequence current are equal in magnitude, but they are flowing into the opposite direction. Clear? Now, from the voltage equation, VB is equivalent to VC plus IB into ZF. VB is equivalent to VC plus IB into ZF. What is the VB? In term of sequence voltage, VA0 plus A square VA1 plus A into VA2. What is the VC? VC is the VA0 plus A VA1 plus A square VA2 plus IB. IB is IA0 plus A square IA1 plus A into IA2 ZF. Clear? Now VA0 and the VA0, they will be cancelled out. So A square minus A VA1, A square minus A VA2. Now IA0 was equivalent to 0, so this is the 0 only. IA2 was minus IA1, this is minus IA1. So it is become A square minus A IA1 into ZF. Now A square minus A will be cancelled out. So you will get the VA1 equivalent to VA2 plus IA1 into ZF. Now we will draw the positive sequence, negative sequence, and zero sequence impedance so that these two equations will be satisfied. Because we all know that IA0 is equivalent to 0, that means the zero sequence network will not come into the picture. IA1 equivalent to IA2, that means you can say if I have a positive sequence network and the negative sequence network, the output of the positive sequence network is a VA1 and current is a IA1. This is VA2 and current is IA2. So IA1 equivalent to minus IA2 means this will be connected, but VA1 is the VA2, VA1 is the VA2 plus IA1 into ZF plus IA1 into ZF means there will be a impedance of ZF here. Connect the positive sequence and negative sequence network through a ZF. So VA1 will be equivalent to VA2 minus IA into ZF. This point is clear. This is my positive sequence network and this is the negative sequence network. So in case of line to line fault, zero sequence network does not come into the picture, and the positive sequence network and the zero sequence network will be connected in parallel with the impedance of ZF, like this, with the impedance of ZF. Positive sequence impedance and the negative sequence impedance connected in parallel with the. Clear? Now the positive sequence network is this E and Z1. A negative sequence network is only Z to ZF. So this is a single loop. What is the value of IA1? Value of IA1 is become EA1 divided by Z1 plus Z2 plus ZF. Generally EA1 is equivalent to 1 angle 0 degree. Z1 plus Z2 plus ZF. This is my IA1 and IA1 is equivalent to the minus IA2. Clear? This is not the fault current. This is the positive sequence current. This is only the positive sequence current. Clear? Now, what is the fault current then? The fault current is equivalent to IB. And what is the IB? So fault current is the IB. Because we know the sequence current, so we can find out the value of fault current. So it is become IA0 plus A square IA1 plus A into IA2. Simple. Now we know that IA0 is equivalent to 0 and IA2 is nothing but the minus IA1. So the value of the fault current is become A square minus A IA1. A square minus A is nothing but the minus J root 3. A is the one angle 120 degree. Always remember. A is one angle 120 degree and A square is a one angle 240 degree. Into IA1 and this is my IA1. 1 angle 0 Z1 plus Z2 plus ZF. So this formula we will use to find out the fault current for a line to line fault. Clear? Okay. Now, if you have to find out the fault MVA for the line to ground fault, this is my fault current. So fault MVA is the root 3 pre-fault voltage into the fault current in actual value. In term of PU, the fault MVA will be direct pre-fault voltage into fault current because root 3 will not come into the picture in case of PU formula of the power. So the MVA PU, the magnitude of the MVA and the magnitude of the fault current, both are the same. So you will use this formula. This is also the fault MVA. Just multiply it by the base MVA. You will get the fault. Clear? Any doubt in this? So in tomorrow class, I will take one example and I will show you how to find out the fault current and the value of phase voltages and the line voltages when the line to line fault will take place into the picture. Always remember, whenever the three-phase fault was occurring, only positive sequence network was coming into the picture. But in case of line to ground fault, all three sequence component was coming into the picture. But for the line to line fault, only positive sequence and the negative sequence was coming into the pictures. So before ending the class, let's do the 2 minutes summary what we have completed today. We have done some question on line to ground fault. Then we have analyzed the power system. For line to line fault, for the line to line fault. Clear? And calculation of fault current, how to find out the calculation of fault current for line to ground fault. Sorry, line to line fault. So in tomorrow class, we will continue our discussion from here. I will solve several questions for the line to line fault, and after that I will move to the double line to ground fault. Any doubt? So thank you everyone.